you to do this exercise. Okay, so this is just exercise for your study group that you can talk about. You can even talk about the N number, the number transfer, oxidation number, from that to that, how many electron transfer. Some people may not even see that, so it functions a good exercise. So the question mark ones are the ones you go to determine by following that theoretical formula. So you need to determine the manganese oxidation number of each chemical all the way to manganese neutral. One day there's a lot of writing pen, and today there's not. I wonder. Okay. Okay, the Nernst equation for half reaction. Now, Nernst equation can be applied to both complete reaction as well as for half reaction. So here, this is obviously a half reaction. So where the obvious comes from, the number electron. Okay, so this is a half reaction. So if you are asked to calculate the experimental potential for this half reaction, specific for this half reaction, then the N, you use 6. So that's the only point I want to make, because we saw previously a complete reaction. So complete reaction N is different than specific for half reaction. Okay? So you can calculate the specific half reactions potential first, and later on combine the two, that becomes the overall. Okay, so you have two ways to do it. One will be based on the complete reaction and get the E overall, and the other way is you separate, the two E's and then combine. Okay. Any question with that? Okay, so now for redox reaction, you're going to use it for titration. So here, you may use an oxidizing agent as titrant. Because it's oxidizing agents, then you're going to titrate for the analyte in the reduced form. In a reduced form only, because this is a redox reaction, right? So the reduced form will get oxidized. Now, in the same solution, so your analyte, some of your analyte could be in the oxidized form. So for that, then you use a reducing agent. So what it amounts to, if you use a reducing agent, only analyte in the oxidized form will be determined. Okay? So we can call the chemical as particular species you are titrating for. Okay? Now, as an example, so I call this speciation is good, for example, chromium 3 plus versus chromium 6 plus. Now this guy is a carcinogen. Well, this is not, so this is an oxidized form and this is a reduced form, right? So isn't it good if you can do speciation titration, right? So in that sense, it's good. At first, I could not spell carcinogen, so cancer where the N come in, but it's carcinogen. Can, C-A-N-C-A-R, you know, so get a little confused. Cancer, and then carcine, oh yeah, carcine, yeah, so R-I. Okay, but in most applications, you will be interested in the total. You don't care of the species, right? Although in this particular case, you know, this is important for speciation. It means more than the total. Okay, so it will be a slow process. If you were interested in the total chromium, that means you're going to do 2 titrations, right? The first one determine that species, the second one for that species and combine. So it's a 2 titration, so it's slow. So once you realize that, you can speed it up, right? Now, because the case is that most titrations, you want to determine the total. You don't care of the species, okay? And you want to speed up the titrations so that 1 titration will do instead of several titrations for the same analyte. Okay, so this is analytical knowledge. So that sets apart what is PChem, what's analytical, what's organic, you know. For analytical, you think along these logical lines. Okay, as an example, in your sample, your analyte is iron, but then iron exists in different oxidation states, right? For example, 2+ and 3+. So you want to speed up, so you want to pre-treat your sample. Okay, pre-treat the sample fast, and of course, analytical chem, quantitative. So you want this to be fast in this sample pre-treatment. The purpose is to change all the oxidation states into 1 only, you know, 1 oxidation state. So you want it fast and quantitative. And therefore, the pretreatment will be a column. A column, you simply pour your sample in, go through a column, then you get your sample ready for titration. So that is fast. And desirably, you want the column to be universal, that can work on as many elements as possible, as many analytes as possible. So this is a desirable feature. So if you could come up with good columns, or chemical columns, then it could carry your name. So now,
unless we're in like Eastern culture, right?
Right. The Eastern culture is that well, universal column, it's not Kin's column. Yeah, but it's okay for science. Okay, so now, you know, after doing this, then you can do redox titration, because now your analyte exists in this oxidation stage only. Okay, so next we're going to look at some of the useful columns available.